Hello everyone, basic of liquid crystal. Title of my talk, and I am going to explain some short brief of liquid crystal in this lecture. As we all know, matter exists in three forms: solid, liquid, gas. In which solid may exist either in crystalline form and in amorphous form. Upon heating, a solid transforms into a isotropic liquid. Again, on cooling, it gets transformed into liquid crystalline phase. There are certain materials which does not directly transform from crystalline phase to isotropic phase or vice versa, but that take on an intermediate structure which they can flow like a liquid with maintaining the anisotropic physical property similar to crystalline solid. This intermediate phase of material termed as liquid crystal, liquid crystalline phase, mesophase or mesomorphic phase, and such materials are called mesogen, liquid crystalline or mesomorphic substance. The molecule in a liquid crystal are ordered, whereas in liquid they are not. The order of in liquid in a crystal is usually both positional and orientational. In that molecules are constant to occupy a specific site in the lattice and to point their molecular axes in a specific direction. The molecule in liquid, on other hand, diffuse randomly throughout the sample container with molecular axes tumbling widely. Many phases with more order than the present in the liquid but less order than typical crystal also exist in the nature. These phases are grouped together and called liquid crystal. Since they share properties normally associated both the liquids and crystal. The molecules in all liquid crystal phases diffuse about much unlike the molecule in the solid, as as they do so, they maintain some degree of orientational order and sometimes a positional order. In liquid crystal phase, one molecular axis tend to point along the preferred or along a preferred direction as the molecule undergoes diffusion. This preferred direction is called director and denoted by the vector, unit vector. This figure shows the molecular order in a chromatic liquid crystal. To specify the amount of orientational order in such liquid crystal phases, an order parameter is defined, which is usually denoted as S, capital S. Let us now calculate S, where there is no orientational order. That is when the molecular axes point in all directions with equal probability. This means that f theta is equal to a constant. Let's set it equal to 1. So S is equal to, this is the formula, and which is reduced to integral minus 1 to 1, 3 by 2 x square minus 1 by 2 dx divided by integral minus 1 to 1 x is equal to 0, where x is cos theta. Thus S is 0 if there is no orientational order. In a typical liquid, S decreases as temperature is raised, taking on the value between zero point 0.3 to zero point 0.8. S is a perfectly oriented system. Types of liquid crystal. Liquid crystals are subdivided into polymeric and monomeric form. Further, the monomeric form are divided into allotropic and thermotropic. Thermotropic liquid crystal has several forms like rod-like, disc-like, banana-like, gobbler, and broad-like. Rod-like is divided into nematic and sematic phase. Disc-like is sematic B M and sematic B phase. Banana-like thermotropic liquid crystal is subdivided into cobbler and nematic. The globular is subdivided into plastic, and the broad-like is subdivided into kinetic. The nematic phase of the calamate, that is rod-like liquid crystal, is simplest crystal phase. In this phase, molecules maintain a preferred orientation direction and they diffuse throughout the sample. There is no positional order in this phase. There is positional order since the center of masses are arranged in layers, and if the director is perpendicular to the layer in which molecules are more likely to be, then it is called symmetric A liquid crystal. If the director make an angle other than 90 degrees to these layers, it is a symmetric C phase, and in these two phases, there is no positional order between the layer. If the molecule that form a liquid crystal phase are chiral, that is the lack of inversion symmetry. The chiral phase exists in place of certain non-chiral phase. In chematic liquid crystal, the nematic phase is replaced by the chiral nematic phase, in which the director rotates in a helical fashion about the axis of perpendicular director. This is a typical example of symmetric A and symmetric C with the positional order. These are the phase diagram for two typical molecules. Like it is solid at 118 degrees centigrade and it maintains the nematic phase up to 135 degrees C and then it's become liquid. And another molecule solid up to 60 degree and then it goes to symmetric C for 3 degree, and then from 63 to 80 it maintains symmetric A. From 80 to 86 it maintains nematic crystalline property, and then it goes to nematic. Then viscotic type. Disc-like molecule form a number of liquid crystal phases. The simplest type is the nematic phase, in which the short axis of the molecule are preferably oriented along the single direction, again called the director. Positional order in discrete liquid crystal display itself by the tendency of molecules to arrange themselves in column. This means that the plane perpendicular to the column, the molecule tend to arrange themselves in two-dimensional lattice, either rectangular or hexagonal. So they diffuse throughout the sample, and this is called the corner phase. This is a typical example of a discotic liquid crystal, whose phase diagram is it is solid up to 152 degrees centigrade, and then up to 168 degrees centigrade it maintains columnar, and then from 168 to 244 degrees centigrade it maintains the nematic phase, and then goes to isotropy. Anisotropy. The property of liquid crystalline crystals that distinguishes them from liquid is a small degree of order among the molecules. The order destroys the isotropy of the liquid crystal. All directions in the liquid are equivalent, produce an isotropy, and all directions in liquid crystal are not equivalent. This anisotropy manifests itself in a elastic, electrical, magnetic, and optical property of material. Measuring the viscosity of a liquid crystal can be done by placing it between two flat plates and measuring the force necessary to move one plate past the other at a certain velocity. The plates lies in xy plane and are separated by a distance d. The bottom plate is fixed and the force acting on the top plate is the x directional fx, and the velocity on the top plate is also The next direction is Vx. This is the example. Force is applied Fx, and in this case, director is perpendicular to the between the plate, and it is parallel in the plate, and again it has the orientational direction. Three situations in which the director of the crystal points along different directions. It is not difficult to imagine the force necessary to move the top plate at the specific velocity is different for each situation. If the if two assumptions are made, namely that the flow is laminar and the velocity of the fluid next to each plate move with the same velocity as the plate, then the general definition of the viscosity as shearing stress divided by the velocity gradient becomes delta is equal to fx by a divided by dvx by dz, which is equal to fxd divided by avx, where a is cross-sectional area of the plate, resulting three viscosity, sometimes called the Mesophase's coefficient, and also called the eta 1 directed perpendicular to the flow direction, eta 2 directed parallel to the flow direction, and 3 directed perpendicular to the flow and perpendicular to the velocity gradient. All these viscosity decreases with increasing temperature, which is quite typical for a liquid fluid. Effect of electric field on anisotropy. Imagine an electric field E is applied to a nematic liquid crystal. This field causes a slight charge separation on the molecules, creating big dipole moments. Since the average dipole moment per molecule is the same direction for each molecule, this dipole moment add together and cause each unit volume of the material to possess a net dipole moment. This dipole moment per unit volume is also called polarization of the material and the point in the same direction as the average molecular dipole moment from negative separated charge to positive separated charge. For a small enough electric field, polarization is proportional to electric field. The constant of proportionality in unit of permeability of free space is called the elastic susceptibility of the material chi c, that is vector P is equal to epsilon 0 chi c vector E, where chi c is the permeability of free space, that is 8.8 into 10 to the power 12 c square by nm square. This diagram shows the polarization electric field in the liquid crystal. N2 director vector parallel to the flow and N3 director vector perpendicular to the flow to the gradient. Calamitic mesophase structure. Liquid crystalline phases have properties which are intermediate between those of fully ordered crystalline solid and the isotropic liquid. Liquid crystalline mesophases are fluid which, due to partial orientational order of the constituent molecule, have material properties such as permeability, refractive index, elasticity, and viscosity, which is anisotropic. That is, their magnitude will differ from one direction to another direction. Possible melting sequence for a liquid crystal material. This shows the melting phase diagram of the liquid crystalline material. Structure of the liquid crystals. The liquid crystal structure is divided into several parts. The main part is core structure. The core can be difficult to define absolutely, but it is usually defined as the rigid unit, which is constructed from linearly linked ring unit. The core is often defined to include any linkage group in any lateral substituent that is connected to the ring. These are the few examples like of the core structure like 1,4-phenyl, 2,5-pyrimidine, 2,6-naphthalene. And there are some cyclohexene type structure also in the core form. Effect of aromatic core change to transition temperature. Just see this structure. There is a change in transition temperature is 17 degree. Here we have a 3.5 degree. This core shows very high change. And this is, for example, at 130 degrees crystalline, and then it forms aromatic to up to 259, 39 degrees. There are more examples like this. One can see and understand that the core has a role in its transition temperature. Then the terminal moiety. Terminal group other than hydrogen are virtually always implied in a liquid crystalline system. The long alkyl or toxic chain adds flexibility to the rigid core structure. They tend to reduce the melting point and allow liquid crystal phase to be exhibited. The core is often defined to include any linkage group. These are few examples of terminal moiety like this. One can see the long alkyl chain, some other alkyl chain. Then the linking group. Linking group are normally those structure units other than direct bond. They connect one part of the core to another part. This is like the structure connect to phenyl ring, and they are called the linking group. There are some examples of the linking group in the liquid crystal. Then the lateral substitution. Wide range of different lateral substitution like fluorine, cyano, NO2, CH3 have been incorporated into many different liquid systems, crystal ecosystem in many different amounts. The lateral substitution is one that is attached off the linear axis of the molecule and usually on the other sides. Lateral substitution, that is the size, it can be small, it can be large. Polarity, it may be polar, it may be not polar. Position, it may be inner core, it can be outer edge on the terminal chain or on linking group like this. Chiral, an object or molecule that is not superimposable on its mirror image is termed as chiral. In most cases, such chirality is generated by there being four different structural moiety attached in a tetrahedral sp3 carbon atom. Like this, you can see there is a chirality maintained. 2-octanol and R2-octanol. Usually the chiral liquid crystal, the helical structure has ability to selectively reflect light of a wavelength equal to that to the helical pitch length. However, the chiral nematic material must be aligned so that the helical axes are parallel to the light propagation direction, and this is showing the direction pitch length. And these are the example of chiral molecule, and they have the orientational direction. Theoretical insight. Landau-Dijon theory, the first theory came, is a phenomenal model of the pneumatic liquid crystal, a pneumatic isotropic phase transition. It's based on the Landau general description of phase transition and was first developed by Dijon. It is a theory that attempts to describe the pneumatic isotropic phase transition rather than calculate the behavior of the system starting from molecular interaction. The Landau-Dijon theory for the nematic isotropic transition start by assuming that the order parameter S is small in the liquid crystal phase in vicinity of the transition, and thus the difference between the free energy per unit volume of the two phases can be expanded in power of ASN. This is the some diagram order parameter as a function of temperature for a specific set of parameter of Landau-Dijon theory. T is the nematic isotropic transition temperature. Next theory is the Mariosopic theory. Mariosopic theory starts that with a simple expression for potential energy Ui theta I of a single molecule in the sea of other molecule. And this is Ui theta I is equal to this parameter where theta is the angle between the long axis of the molecule and director, and V is the volume of the sample, and A is the constant independent of temperature. This is the order parameter as a function of temperature for the Mario liquid crystal technology. Nematic liquid crystal display. Linearly polarized light traveling along the axis of the chiral nematic liquid crystal is rotated, remaining parallel to the director. If the pitch of the chiral nematic is much larger than the wavelength of the light, and if the wavelength is not too large, the waveguide regime is used in the most popular liquid crystal display, the twisted nematic LCDs. This is the typical arrangement of the liquid crystalline display cell. Acknowledgement, Professor Sopti, Professor Mir Chaudhary, my PhD supervisor, then the first postdoc supervisor, Professor Susan and Walter T. The second postdoc doctor, friends G.N. Sastry, C.V. Sastry, Sam D. Wizard, and Etienne Derat. Thank you for your time. I hope I must be able to give you a clear information about the liquid crystal.